Hi, everybody. Welcome to another round of IRIS-HEP Fellows Talks. We have quite a few of them today, um, uh, so welcome. First up is Jack. Jack, you want to go ahead and share your screen?
All right. Can I start?
Sure. Go right ahead.
Okay. All right. There we go. All right. Hello. Thank you for having me. My talk today is going to be on one flow to unfold them all. And this is mentored by Massimiliano Galli. So just a little about me. I graduated this May from physics undergrad at Purdue, and I'm currently a first year PhD student. I worked for 2 years, and continue to work in Professor Mialou's research group on high energy physics ML applications. And I'm currently working on normalizing flows research for unfolding under Massimiliano Galli and his collaborators. So little rundown of unfolding. So unfolding is effectively the process of correcting observables that we reconstruct via the detector in the Large Hadron Collider to get the truth observables, right? Like any experiment, we are limited by technology. We always have a finite resolution. And so we can try to use ML to correct this. And it's actually very good for unfolding. And this is a highly non-trivial problem. It's important for all LHC analyses. I mean, whenever you get data, you need to unfold it to correct for detector effects. Yeah, and so how was this done previously? The earlier analytical modeling, so non-computational, kind of just took detector effects as a response matrix, calibrating some weighting matrix. Basic, you get your data, you put it into a feature, and then you multiply by matrix, you get corrected features that are weighted. So we introduced normalizing flows for nonlinear yet invertible mapping from reconstructed data to truth observables. And so how do we specifically do this? So we pass our features with some conditioning variable. It's binary, it's a 1 or a 0, which represents which distribution space to map to. So we have two mappings, right? We have simulation to base, so this base distribution, and then we have our base to data. This will also be referenced as Reco to base and base to gen, or truth, which is what we want. Mappings can be composed, right, since they are invertible, to give one invertible mapping. So we can just have a direct Reco to truth particle mapping. And so that is the ultimate goal of this project is to develop just this unfolding framework for a single flow with a Boolean variable as a condition that would be cheap and efficient and interpretable. Thanks to its invertibility, it is interpretable much more than most neural networks now. Yeah, whether it is cheap, well, it is cheap. The model we use is fairly small. Efficient, you can decide that for yourself. So just some baseline performance on Z-jets. Yeah, so our reconstruction, like what our detector would see, is in blue, and our predictions are in green, and just gen, right, truth, is in red. And we can see that, especially in the low PT, low mass regions, we perform significantly better than the reconstructed algorithm. We do vary a bit. We start to diverge on the high mass and PT, but this is just because we have low statistics in those areas. And this is just another with TTH next to leading order, which is just another process. And we can see that our unfolding performance is still pretty good in these areas. So now we come to the problem. So the downside to distribution level sampling, right, which is how you would get predictions from a normalizing flow, is that the individual unfolded observables are likely to be displaced from their gen counterparts, right? Because you are just sampling from a distribution. It doesn't matter if it's, analytical or learned, data-driven. I mean, you are just sampling. So how do we enforce this event-wise accuracy while keeping our nice, pretty distribution level agreement that I showed previously? So in this presentation, I show some attempts of mine to answer this question. So what are we trying to do? Maybe in a little more quantitative form. So we want to balance this NLO loss, which is effectively our classification, multi-class classification loss, that is mainly what we backpropagate on to get all these. It is the main loss, the primary loss. And we want some other penalizing term for this event-wise discrepancy, right? So L1 or L2, which if you're not aware is just difference or difference squared. We do this by introducing a total Lagrangian, you could call it. You can kind of think of it as Lagrange multipliers, constrained optimization, however you want to think about it. So the main, I guess, thing we try to introduce here is, so this G would be our L1 or L2. So we have some damping scaling, all right? So we have G squared, which represents that we ultimately want to reduce this loss, which is scaled by rho. And we have our lambda, which is an adaptive regularization parameter to try to balance F and G. So this optimizer, like any neural network, will try to minimize this loss, and lambda will try to adaptively enforce G in the presence of F as training goes on. So how do we do this specifically? So there's two ways to formulate the G. So we call this quant or prob. Quantities, we sample the quantities from the flow, and we keep the truth as our truth, as our y, right? So X is predicted, Y is truth. Simple. Probabilities is we take the conditional probabilities given our truth distribution of unfolded and truth, because ideally the probabilities of the bins, right, should be the same. So there's kind of two ways to do that. In addition, there's two ways to enforce G via this Lagrangian. There's two ways to treat lambda. No grad would be when you increment lambda on a schedule, taking into account your accumulated loss. So if your loss is high, then lambda gets bigger. If your loss is decreased, lambda will start to plateau. Grad is effectively when you make lambda a learnable parameter, which is also known as MDMM, modified differential multiplier method. So yeah, is lambda being backpropagated on? That's kind of just the difference between these. So how do we measure these? So for distributions, I mean, I personally like Wasserstein distance, also called Earth movers distance. It's effectively just the amount of work needed to transform one distribution to another. So you imagine you have two piles of dirt. How much dirt would you have to move to make one pile look like the other? And there's a long, complicated integral expression, but that's how I like to think about it. And because we're comparing to RECA, we take this ratio of our distance between pred and truth and RECA and truth. So that way we're comparing to our detector response. Per event similarity can be measured by a response matrix diagonality metric. So you have a bunch of bins. So it's the bottom picture. You have a bunch of bins, right? You say your truth is in some bin. Your unfolded should be in the same bin. So obviously you want this matrix to be diagonalized, right? This formulating a metric for matrix diagonalization is pretty easy. You could just take the ratio to how much is in the diagonal versus how much is in the total matrix. So this goes from 0 to 1. 1 is perfect, 0 is very bad. So when running this, the results we get are fairly interesting. Quant no grad ends up winning. We could see that prob overall does a lot worse, especially when prob has a grad, right? We make our enforcement learnable. In general, grad does a little worse, and I'll explain that in a moment. So the results, when we visualize this, right, we have this -6 here for a special bin, because occasionally in high energy physics, we make selection cuts, and if they don't pass that, then we put them in our -6, right, our special bin. So some of these were misclassified. So when we apply these quant no grad corrections, or this loss, we can see that these disappear, and we get a little more diagonalization. You'll see some of the numbers in the middle start to bump up a little, which is good. That's what we want. And so, like, obviously, when you do this, there's going to be a trade-off, right? Normalizing flows are primarily used for density estimation. So, does this ruin our distribution? Good question. So we can see that in the low PT, and this is for mass also, they kind of follow the same pattern. We get a little better in, we're still better in low PT marginally, and this obviously starts to diverge, yeah, which is kind of expected. Can we reduce this trade-off? Probably with hyperparameter tuning. Yeah, so rho, and then like, can we improve this regularization via model scaling? Does our model scale well to get better predictions? That's another question we have. But overall, it's very interesting to see that applying this hard constraint, right, where lambda has to minimize G via backprop, it completely throws off distribution similarity to the point where they're just not compatible, which I think is expected given the nature of normalizing flows. We also see that in general, the quantitative method performs significantly better. Most likely, since we are regressing on physical quantities, right, the actual physical predictions of the model and not just conditional probabilities. Yeah, so I think in general, these results are more or less expected. It's kind of weird to see that. Well, I mean, I guess it is a little expected to see that grad, right, trying to enforce an event-wise loss in a density estimation model more or less throws it off. But yeah, this is very interesting to see, and I'm very excited to see how far I can take these numbers. Yeah, and that's my talk. Thank you. Questions, comments, concerns?
Thank you, Jack. Any questions for Jack? All right. Interesting talk. Up next is Ivan.
Yeah, can you hear me?
Yes.
Okay. Can you screen?
Yeah, we can see your screen whenever you're ready.
Hello, everyone. I'm second year master's student in high energy physics at the Russian International University of Kyiv. My topic for this project was Alpaka benchmarks for CMS pixel track reconstruction. What is Alpaka? Alpaka is essentially a portable layer written in pure C++. You can compile the same source code for different accelerators, and like CPUs, GPUs, and even FPGAs. And that's crucial for LHC experiments where clusters are a patchwork of vendor hardware. As I know, PixelTrack already benefits from Alpaka, but the upcoming short version of this library is major rewrite. So we need quantitative benchmarks to be sure CMS can switch without any surprises. In a typical project, we have two basic gates. The code compiles and a unit test pass that tells us the code is correct, but it does not tell us if a commit made the library faster, slower, it improved, or made worse performance, especially across different backends, CPU, GPU, and different compilers. With the ongoing Alpaka version 3 API refactor, the risk of silent performance regression is real. So our goal was to build a continuous integration ready benchmarking system, standardized executable with clean CLI, CSV output, registration with test, and etc. The key is reproducibility on common yields component numbers across machines. My role was to deliver one of the first building blocks. I started with a memory allocation micro benchmark to get fluent with the new Alpaka sort API. And after that, I ported a mini-builder benchmark, a realistic arithmetic workload, and run matrices on PVI and PG size parameters. I'll talk about this later. Collect CSV and render reports. Performance tuning was a bonus. The primary objective was reliable numbers. I began with allocation benchmark. My first measurements looked great, and that was a problem. They were dominated by a lazy allocation. The operational system reserves virtual address space, but the physical memory is only committed on first touch. And if we time malloc or CUDA malloc without touching data, we get misleadingly small numbers. To fix this, I used memset and touch memory from Alpaka library. So we truly back the allocation with physical memory. Also, I split timing into a short war up to eliminate cold start effects. And the kernel section, here we actually benchmark. Then I standardized and wired the target into C-test. Along that way, I learned that the essential of Alpaka sort, device selection, quiz, buffers, walk division, which paid off when moving to mini-builder benchmark. Next, I'll show how these ideas map to the mini app. But before that, I can show you two plots. These are the final results from the memory allocation micro benchmark. On the left, we can see GPU allocation. After fixing lazy allocation, bandwidth stabilize about 130 gigabytes per second for large buffers, which matches the expected range for device memory initialization on RTX plus hardware. And on the right, CPU results are around 2 gigabytes per second and mostly flat, which is consistent with main memory commit latency. After the allocation benchmark, I moved to mini-builder mini app, which is realistic scientific workload, a simplified molecular docking kernel. It's widely used in performance studies for COCOS, OpenMP libraries, and some other. So it's an ideal candidate for comparison in our library. My job was to port this mini app to Alpaka, keeping the structure close to the original, but abstracting the compute and memory layers. I also added a memory line interface CSV output and after tuning mechanism from original benchmark that sweeps through different threads per port item, PPY parameter, and work group size, which is parameter automatically. The main goal was not only to run it, but to produce reproducible, comparable performance data for each backend under the same configuration. Later, I started optimizing it as a bonus track to explore how different transformation affect the Alpaka backends. Here are the performance comparison of the different kernels variants relative to the upstream version. I implemented several optimization strategies: memory alignment, loop unrolling, FMA, full vectorizations in course or fast. You can see it on the plot, and some of them give us improvements of performance, and some of them not. Here I compare the CPU version with and without PPI vectorization. I plot throughput in giga interaction per second, and higher is better. On CPU, the gains are modest. Vectorization don't help a lot at a low PPI, and then both version converges as PPI grows. That's maybe expected. Our CPU backends serial at OpenMP blocks effectively run with register size 1, so register level sync doesn't translate into big block level wins. Still, it's a safe optimization, not correctness issues and no large regression, so we keep it available to after tuner. There are heat maps for the full sweep of two parameters, PPVI and feature size, on an A40 virtual machine. Left is our Alpaka port, and right is the original mini builder. The color is on log scale, so dark cells mark the fast regions, and numbers in the cell is normalized results. So 0 is the best results, and 100 is the worst one. And when we look at these plots, we can notice two things. First, both show a valley of good performance, but location at widths of the optimum differ. Our sweet spot is around 460, and VG size 1.4 PPI, and VG size 32,188, while the original has a deeper minimum on PPI 4 and VG size 32. This demonstrates the difference between our implementation and the original, and requires more precise investigation. Is it caused by the use of a library or an inaccurate of my implementation of the benchmark? So we still need to investigate. Here we collapse the heat map by taking for each PPVI the best reach size and plotting the speed up against the original CUDA version. On this machine, we are consistently above 1 for mid to high PPVI, and that demonstrates that our implementation of benchmark is still much slower for some of PPVI than original upstream one. up to 7th time. On Titan, I run two different implementation of benchmark, vectorization, and new is without vectorization, because on some runs vectorization will give us worse result than without, and firstly we think that vectorization made our performance worse than without, but on big comparison, big runs, we can now see that actually vectorized by PPVI, we have speed up from 2 to 4 for different PPVIs. And for the last one, we have slow up. We still don't know why. So, conclusions. I delivered two working benchmarks, memory allocation and mini-builder. The mini-builder port uses a single Alpaka kernel with serial backends, exposes PPVI and VG size as auto-tuning parameters, and comes with a script to sweep, export CSV file, and visualize results. On the performance side, CPU gains are moderate. On GPU, the Alpaka port is often competitive and sometimes faster than the original implementation for some of PPVI parameters. We also identified negative interaction like FMA in specific settings, which already serve as feedback to improve the library or to improve benchmark implementation. They still need to investigate. Next steps could be to further improve auto-tuning and documentation, as well as help integrate these results into a broader performance dashboard. So, thank you for your attention.
Thank you, Ivan. Any questions for Ivan? No. All right. Thanks again. Next up is Dmytro Belytskyi.
Yes, I'm here. Can you see my screen? Not yet.
Give it a second.
Here.
Yeah, we can see your screen.
Okay, good. So I will start. I'm glad to present today the project luminosity studies on the first level trigger data of the CMS experiment at the high luminosity Large Hadron Collider at full 40 MHz. My mentors are Alexey Shevelev and Elena Korecheban. So, as you probably know, LHC is largest world collider built somewhere around 2008, and CMS is one of 4 major experiments at the LHC ring. Well, so during the project, I worked with members of the Brill group. Brill group stands for beam radiation, instrumentation, and luminosity. The main goal of the group is to estimate beam parameters. Well, one of these parameters is luminosity, and luminosity was the main objective of this work. Well, so what is luminosity? Basically, it's just the ratio between the cross-section and production rate inside the ladder. Why is it important? Well, this follows from that. This is ratio between cross-section. If you want to measure cross-section and in experiments, we need to know luminosity with great precision. Well, good. So, why we here have a problem? The issue is that, like lab in LHC, it doesn't have any reference process to use it as direct measure of luminosity. We have some instrumentations, call it luminometers, which provide us with measurements of luminosity, actual luminosity. The problem is the precision isn't close enough what we want to achieve. It's declared that the target error, relative error, is around 1%. That's what we want to get, but in reality, it's like 1.4, 1.6. Well, to make matters worse, next years, the LHC will be closer to the upgrade, and well, it will be upgraded to provide high match luminosity, high match pile up, and as a result, much larger luminosity. Problem is nonlinear effects and noise scale very much with pile up, goes very up, and as a result, we will get big degradation of performance. So right now we need to come up with something to mitigate these issues. Yes. So luckily for us, one of the options is to use data from the detector itself. Well, high-level data is unusable as it's biased. It's biased by the trigger decision. Luckily, we could use the data from the trigger itself. It's called inline scouting, and it was run already as a demonstration, and we have all the recordings of the events, which was used in this research. Well, so the idea is that some events from this well-known trigger, they are directly proportional to the luminosity, and so we do some calibration, we could use that to estimate luminosity with high precision. This is it. So now we have three main objects. It's jets, it's muon stubs, and yagams. So my task was to analyze what properties this object have and which of them are the best suited for the purpose of luminometers. Well, as you could see this plot here, well, I should mention that, yes, in LHC we have two particle beams which rotate in the opposite direction, and these beams are not continuous. They consist from the bunches, and when bunch crosses, we have collisions, and then there's like should be flat space. However, as we could see here, we have a lot of noise between places where bunch collide. Well, and this noise obstruct our observation, and the first task was to filter noise somehow. So I analyzed different variables what we have and determined that the most suitable is use filter events by energy. Well, it's trivial, but it works somehow. So I do some cuts and I measured signal to noise ratio. You could see plots here, and from that I determined that, well, the best candidate is muon, as we have the highest signal to noise ratio without any cuts. Well, so we go further with muons. Well, good. So what I worked before this, like this whole calculation, this was done on one file from many. Like run consists of, it's slightly pre-processed data, it's root files, but it's still what we had directly from detector. Okay, so I work with one file, and then it's like one file is like one of my section is 23 seconds of data. Well, then to see some change in data, this was big step forward because I run calculation not on bio file, but on something like 2000 is equal to 8 hours of raw data from detector. And what you could see here is simple image of how muon concentration change during time in detector. It is related to luminosity. It's not luminometer yet because we don't know scale, but it is lumiscope. We probably could say it. Well, so what currently I'm at this point, and the next step is to do calibration, and that's what work is going further beyond the project of IRIS-HEP with my mentors. That's it. We will do some calibration with VDM scans, and hopefully we'll get the direct luminosity measurements, compare it with real values, not real, with what we measure from other luminometers, and get estimation how this method works, how good it is, how bad. That's it. Questions?
Thank you, Dmytro. Any questions for Dmytro? Next up is Kyrylo.
Okay, hello.
Yep.
Do you see my screen?
Yeah, we can now.
Yeah. 1 second.
Sure.
Okay. 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 Hello, everyone. I'm glad to be here today. My name is Kyrylo Filonenko. I'm from Tarashchenko Kyiv National University, and my mentor on this project is Valeria Lukashenko from University of Zurich. The main theme of my work is tracking low momentum taus in CMS. What is CMS? It's a compact muon solenoid. It is located in Cem, near Cézy in France. Its main goals are studying Higgs boson, standard model, and physics beyond standard model. It is quite big detector, and it also has a big magnetic field in it. It is CMS. It's also a big collaboration. It has more than 5,000 scientists and more than 50 countries participated in it. Why low momentum tau-leptons are important for us? First of all, is physics motivation. We have a lot of key processes when with low momentum tau-leptons under 50 GeV. And also with these taus, we may study a lot of new physics with low mass and compressed mass. Also in run 2, we had observations like standard hadronic tower reconstruction loses efficiency for momentum lower than 20 GeVs, and improving low towers and identification extends CMS reach and reduce systematic uncertainties in precision measurements. So on this slide, we also may see diagram. This is our main benchmark decay Bemazon into Castar and lepton anti-lepton pair. The key idea of this study is understanding and reconstruction low towers, low momentum towers, and it will be very helpful in future. Okay, so why is it difficult to identify? First of all, is ground rejection. There are a lot of processes that can mimic T signatures, so it is make harder to identify those. On this slide, we also can see one example of reconstruction in CMS. Second, it's trigger elimination. So it makes sense because if particle has less energy, it will be harder for us to see it. I don't find a good picture for this slide, so let's go next. Also maintaining efficiency under high pileup conditions. For example, for run 2, pileup is about 65, and for run 3 is about 60. And we can see a picture on the slide. It was made on 8th of October this year, and it has more than 2,000 vertices, primary vertices, and so it's also a challenge to find tau in this amount of vertices. Okay, next. My goal on this internship was to develop and prepare a machine learning based low tau tagger for CMS round 3. So it was an ABC net for run 2, and my main goal was to adapt it for run 3. And here is my steps. So it was my first work with machine learning. So I should study modern machine learning methods, especially relevant to particle physics. Also understand the ABCNet architecture and adapt it for tau tagging. As said, it was made for run 2. Also identify and resolve issues in signal reconstructions, and dataset preparation. And one of the last is produce an optimized dataset for training and validation for the model. And the main was to train the model and try to see some results. First, my step was the first problem we encountered was problem of signal reconstruction. There are some of problems. For example, missing particles. Beam zones occasionally absent from reconstruction. Next is misidentified resonance Castars mesons often reconstructed incorrectly, incorrect mass resolution, and non-optimized reconstruction algorithm. So that generation took a huge amount of time. When I said huge, it means really huge. For example, we generated 5 events for for more than 5 hours, I guess. So it will take a lot of time to generate data set for machine learning training. Okay. Sorry. New optimized reconstruction algorithm was developed and capable of generating physically valid, high-quality datasets suitable for ML training. Okay. Our variables that we use in reconstruction and training was observed rapidity of the track at the beam spot, azimuthal and angle of the track at the origin, natural logarithm of the track transverse momentum. It was also like pure transverse momentum, but it's more effective to use logarithm. Also, there was a difference in z between track and tagged primary vertex. Minimal of this variable, and also Doka is distance of closest approach to the Kasta vertex. 2D is like xy plane of this variable. So why we choose these parameters? Because this set was used in a previous study. So we decided not to change the choice, but it was necessary to check the optimality of these parameters. We built matrix of correlation of these parameters, and we see that only Doka 3D and is correlated with Doka 2D, and therefore only one of these quantities will actually be relevant for use in machine learning. And the other parameters are not correlated, I can say at all, except minimum delta z and delta z and logarithm of momentum. Therefore a fairly good choice for training the neural network. The main idea is what we saw from matrix, that most discriminative are delta z, minimum of delta z, and Doka parameters. Eta and phi have low standalone power, but contribute in combination. Also, as I say, strong correlation between Doka and Doka 2D. So we may throughout one of them, but we keep it as we. The selected set provides high discriminative power and good feature independence, as we saw on slide before. Okay, so this is a scheme of ABCNet architecture, and this architecture combines graph attention pooling with multi-level features aggregation, and also global descriptions to perform per point classification on point clouds. We have an input. Because my mouse. Okay. In input we have cloud of size and multiply 8. Each point has 8 features. Next, our model starts with gap layer that build local graphs of about on this scheme we have 50 neighbors, but in original code we use 10 and 20 of neighbors. and uses attention to weights their importance. Also, each point learns from its local neighborhoods, so rather than being treated independently. After the first gap block, the network separates into two streams: attention features and graph features, each passing through several fully connected layers of size pointed on the slide. The second gap layer repeats this process with 60, also with fully connected layers. Okay, and all these intermediate outputs from these layers are then aggregated together. This aggregation combines information from multiple levels of abstraction. Also, in parallel, network also processes global features, like, for example, session level or contextual data through a small fully connected layer and merges them into the aggregation as well. Also, the aggregated representation is then passed through a full connected layer and followed by aggregate booleans stabilize the features. And final part of network is multi-layer perceptron, like three fully connected blocks of 256 units with dropout 0.6 for regularization. We use this for not to constrain all our attention on some of neurons, so we can turn off some of them to take another one for our computing. And ending of network is softmax output, given class probabilities for each point. What we did to improve this code and optimize it for run 3. The main improvements are reorganization training pileup. It was divided into several steps: data generation, data preparation for training, and the last one is launch into training. Also, enhanced target handling, predicted values of prediction are now stored as probabilities instead of binary classes. So it's enabling more accurate work and evaluation. Next is refined metric computation. It's we now may solve per epoch accuracy and signal background efficiencies for each epoch, and also robust model checkpointing, automatic saving of the best performing model using and monitoring validation loss. This is training samples and training characteristics. There are some of them. The main take of this slide, that is our single process, is Bimazon into Castar and tau anti-tau and tau anti-tau pair. Background, it is a mixture of QCD multi-jets, misidentified Castars, and non-tau hadronic case that mimic tau signatures. And we can also see that number of events in signal dataset and background are very different. In fact, we don't we want to create a big amount of signal events, but we don't have enough time for that, and that's why we like we retrain our model in the near future when dataset will be ready. So this is output plots. Here we can see dependence of classification accuracy and loss on the training epoch. The blue line is training data, and the orange line is validation data. In this graph, we see that the model learns very quickly, and the accuracy and loss line reaches a plateau. But the first thing that catches my eye, especially here, is that curve jumps up and down during validation, orange line. But these jumps are less than 1%, and it's cannot be systematic since so it just it's just fluctuations. This is a ROC curve of our training. So it's indeed the model learns very quickly and accurately. However, it should be remembered that this training was performed with an unbalanced number of signal and background events. So we will test this model on a larger sample data when it will be ready. So conclusions of our work: the loss function decreased steadily during the first 15-20 epochs and then stabilized. So it is also, we may see that on our plots. Validation accuracy and ROC reached a plateau. With small fluctuations, it's less than 1%. So it's we indeed we couldn't say actually it's our training or not, because we should have more bigger data set of signal processes. And also early stopping triggered around epoch 20 for most runs, so suggesting good convergence stability. Also, I put some data in a table, but there is for a small data set, and we need to make it larger. And like steps for improvement, it is first of all feature level improvements. It's expand input sent to include track quality variables and vertex probability. Model level advancements. It is indeed this network had a lot of like parts from like 5 years ago, so it's it will be good to adapt it for not only for like modern data, but also for modern computing technologies. Training optimization, it's like a parallelized training with mixed precision and multi-GPU execution. It's also in this model we may use, we may put only one GPU. We may choose which one exactly, but cannot take multiple of them. So thank you for your attention.
Thank you, Kyrylo. Any questions or comments? All right. Thanks again. Up next is Luka.
Thank you.
Yeah, hello.
Hi, Luka.
Sharing my screen.
Okay.
So let's begin.
Okay.
My name is Gavrysh Luka. I'm the first year master student at Taras Shevchenko National University of Kyiv. I'm currently working in Boston University group at the CMS experiment under the supervision of Serhiy Chulak and Zainet Demiragli. My project title is the software development for the inner tracker data trigger and collect system for the CMS phase 2 inner tracker. So let's begin and see that how the inner tracker itself will is being built for the future high luminosity phase. Basically, the tracker in the CMS experiment is divided into two parts, outer and inner tracker. So it is designed to perform under the extreme conditions, including the pile up to 200 collisions per bunch crossing, extreme radiational levels around 1.2 grad TID, and heat rates exceeding 3 GHz per centimeter squared. The main structure, as you can see on the right, we have a 1/4 slice representation, and this geometry is visible as a quadrant of concernic and radial pixels layers that together make up a fully cylindrical detection volume. We have three main parts of this tracker. We have 4 barrel layers or TB peaks. It's modules that will surround the beamline with a fine granularity. 8 forward disks, TF peaks. Basically, they're mounted perpendicular to the beam axis, capturing the forward region particles. And the last one is 4 end cap disks or TAPX, which extend coverage into even more forward region. So the main detector at the CMS phase 2 will be used the pixel detectors represented by the RD53AB chips. Basically, we have 2 different silicon sensors. We can have them squared, 50 times 50 micrometers squared, or rectangular, 25 times 100 micrometers squared. And sensors are either planar or 3D, with the 3D variant is used in innermost layers due to its superior radiational hardness. So let's dive a bit deeper into a data chain that will be used in the future experiments. So everything starts from the readout chips, as I said. The RD53 chip detects the charged particle, hits on the sensor, amplifies the signal, and digitalizes it. Basically, this chip, it's a matrix that consists from 432 pixels times 336 pixels, and it is implemented in 65 nanometers MOS technology. Then the data and chips itself performs zero suppression, keeping only relevant hit data. Then the data are transmitted via high-speed serial lanes to the LPGBT ASICs. What is the LPGBT? Basically, it's a low-power gigabit transceiver. It's also a radiation-hard high-speed ASIC developed at CERN for data transmission and control in high-luminosity LHC detector systems. It acts like a communication bridge between the front-end electronics, as a readout chips in our case, and the backend systems like the Apollo. But what also LPGBT chip does, it also aggregates up to 3 RD53 streams and send them optically to Apollo board. What is Apollo board? It's like a control module in this scheme. And we can see that it is divided into 2 huge parts. First one, it is the command module. It is a module that is equipped with the 2 FPGA boards. The command module handles high-speed optical data from the LPGBT links that supports up to 72 LPGBT inputs for 10 gigabytes per second each, 16 links for 25 gigabytes links to the central DAQ system, and from 4 to 8 25 gigabytes per second links dedicated to real and level 1 trigger system. And the service module, it's a Linux-based embedded system running on Zing. It manages power distribution, clocking, slow control, and communication via Ethernet and IPMI. So Apollo board, Apollo's common module receives the data, performs packet parsing, event building, and either stores the forward to the queue and the trigger logic. And it's a final stage of the data chain. It is important for us, as my first task was the module map reader. I started talking about it on my lightning talk, and I've successfully finished it. What is module map reader tool and why it is important? So basically, as you can see on the top, we have 12 different module types that will be used, as I said, in different layers, TBPX, TFPX, and TEPX, and 2 more modules for test, like a single chip card and TPX itself. So to work with the connections and to implement the decoding from the firmware connections to the software, I use the HL library. It's a universal hardware access library. It's basically a C++ or Python software interface that is used to read and write the FPGA registers in a structured and portable way. And the IP bus protocol, it's a protocol and firmware system developed at CERN for slow control of FPGA-based hardware over the Ethernet. So the tool that I've built enumerates links and modules, resolves for each link LPGBT ID and EMP channel, and for every module reports the module type. Then it was a bit of reverse engineering as we were decoding the module name and taking the number of chips in it, as we can get only module chip and the link address. And mostly this was an address that I was trying to get. And for each the module, we get all the chips in it. And for each chip, we get a downlink and uplink. I'll tell you about them later. And for the group, for the down and uplinks, we get the group and channel. So the second part of this task was to work with the module configurations. To the right, you can see that the connections between the modules in CERN, basically at the CMS. But it's not enough to connect them manually. You also need to let the system knows how do they work between each other. So I've made a small scheme, so you can see the connections that we have starting from Apollo blade and with the modules, front-end modules, basically, and something is marked red here. Why it is marked red is just because it's not implemented in the firmware yet. And that's why the configuration right now is done by the methods that are used. They're being done from the hardware description using the JSON files. So it's a small hard coding, but we worked on it a lot. And they did a lot of functions such as the invert, phase select, channel group, or all the information about each chip that is connected to a module. And these methods were used on the Brill test beam this August. Also, during this issue, I worked with, I've created 12 classes for each modules, and the factory that adds all information about the chip to a module, and use this factory to create a hardware description in the software. So my second task was like a preparation for my ongoing task right now. Basically, as I said already, the new detectors that would be used in the CMS phase 2 upgrade are pixel detectors. So a single RD53 pixel can carries 8 bits of configuration, splits into a mask 3 bits and the TDAC 5 bits. The mask has 3 switches: enable, it turns the pixel on off, inject, allows test charge injection, and hit bus route the hit to the bus. While TDAC finally trims the threshold so many pixels can be equalized. The diagram traces the full pass a command takes via pixel portal, the way we are writing to this pixel matrix through the software. The chip's window for addressing the column pair of pixel row by row module controller triggers RD53 command processor and asks for the prepare and process commands method that collects modified registers. For each RD53, it creates an RD53 encoder, runs prepare write commands, and hands the encoder the list of changes. At this point, my work adds the decision and cite encode write to chip. So if pixel portal data are being written and the write long toggle is off, then it uses the manual methods writing row by row that were created before. So if the toggle is on, the encoder switches to a fast two-burst pass that still use the pix portal but sends compact row-wise write long packets. First all mask rows and then all TDAC rows. Internally, I added packing routines that for every row of column pair convert the 16-bit left-right pixel word into 10-bit words, one carrying just 3 mask bits for left and right, and one carrying the 2 5-bit TDAC values. They reduce bus traffic dramatically, as it has. I also made a bench coder, but I'm gonna tell you a bit later about it. We also measured how many it divides number of commands in 2 times actually. So after encoding, commands enter the command queue, which inserts the periodic sync, packs 16 bits into 32 bits words, prepare a link header, splits the streams into safe chunks for the firmware FIFO, and checks hardware status flags. Optional readback, use the pixel portal too. And when pix portal is ready, the software module updates both the portal value and the corresponding pixel column pair. For calibration workflows, I added 1/2 pipelines, prepare and process mask and prepare and process TDAC. So you can update only mask or TDAC by design. Mask only pass does not alter TDAC, which remains staged in the software module until its own pass. So finally, I built the end-to-end benchmark and validation on a small test for 10 column pairs. The new write long methods, as you can see on the screen from my terminal, takes, so the old method takes around 40 milliseconds. Against the new method, they take only 20 milliseconds. So it reduced, decreased encode time twice. And this was like a small preparation, as I said already, for my final task, a calibration. Basically, I've got the latency scan calibration. What is the latency itself? The latency scan is a calibration that determines for each RD53 chip the time of set in bunch crossings between when the charge deposition occurs in the sensor and when the triggers arrives, so that the heat is still present in the chip's readout buffer. So we can think about it, align 2 clocks, the heat time and the trigger time. For chosen latency, we effectively can have a strict formula that time of heat equal the difference between time of trigger reaction minus the latency. Why it is important for us to measure the latency? First of all, if the latency is too low, the trigger looks too early, so heats have not yet reached in the buffer, so we have a low occupancy. If the latency is too high, the trigger comes too late, heats were already dropped from the buffer, so it's a low occupancy as well. Here we can have only latency values are between 0 and 511, as it's like a 9-bit chip limitation for it. So the method, I'm measuring the latency. First, I fix the injection conditions, so they stay constant during the scan. I'm selecting injection type. We can have analog or digital. Set we call higher met to define the target charge, define raw and masks, excluding the dead deliberately masked pixels, choosing number of events. Number, basically it's a number of injections per pixel at each latency settings. And then we're starting to sweep the latency from latency start to latency stop parameters. We have them with a step of n trigger x events. So n trigger x events acts like a resolution, smaller step, basically finer search but longer runtime. At each latency value, we are running the main calibration. run pixel alive scan to collect hits under the fixed conditions. We are computing the average occupancy in the ROI for each chip, ignoring masks and dead pixels, and recording the point. Then the outcome that we'll get, we can choose we're getting the latency for each chip, picking it the maximum for maximum occupancy. If there's a plateau, pick the lowest latency within the plateau, basically. And the output that I'm expecting to have right now, it's latency curve. I have to the right that are taken from documentation. As I'm on a stage right now, I have a work in progress class development and adaptation and the app development for a measurement. So on the right, you can see the so this plot shows the average pixel occupancy for each of the tested latencies. The peak is in the plot indicates the beam at the best or most common value for the latency of the chip. The low occupancy noise in the bottom of this plot is aggregated for the sake of just an example. It is so what we are going to do. Basically, you can see latency here. Just we will see the latency basically at the maximum, and it should be equal 1 here. Everything else, it's a noise. So as I said, I have a work in progress this issue, and I expect to test it during the next week, I hope. So let's have a small summary during the 2 presentations that we had in summer and now. First that I've done, I contributed to the software documentation and some writing some scripts for the software and working on the Apollo boards, aided module map reader and configuration system. I actually added the links to the closed merge request. Implemented and tested the RD53 chip encoder method, and I have an ongoing task that it's a developing latency scan calibration for RD53 chips that contains latency scan app and class. It's gonna be all for me. Thanks a lot for attention. Any questions?
Any questions or comments? All right, thank you.
Yeah.
Next up is Dmytro.
Yep, I'm here.
Okay.
Just a second. Okay, so I hope you can see my screen.
Yep.
Wonderful. So, hello everyone. My name is Dmytro Skorubskyi, and it's a great pleasure to be here today and present my project AGC-RDF on REANA, a RECAST-like reinterpretation workflow with NanoAOD. This work was done under the mentorship of Oksana Shandura, Alex Held, and Palabi Das. So let me start with a bit of background. So the Root Analysis Grand Challenge, or AGC, is a benchmark framework designed to demonstrate how scalable, declarative higher energy physics analyses can be built using modern root tools. It provides well-defined analysis pipelines that can serve as a standard for reproducible HEP workflows. The goal of my project was to bring this analysis framework to the REANA platform, enabling full reproducibility, scalability, and eventually reinterpretation capabilities similar to what the RECAST framework provides. The main idea behind RECAST-like reinterpretation is to decouple the physics model from the analysis logic. Instead of modifying analysis code every time we test a new model, we can provide model parameters via simple configuration. Then the analysis can be automatically rerun to produce updated statistical results without changing the core code. This concept is especially powerful for open data analyses where community members could later reinterpret results under new physics hypotheses. So, in practice, the project consisted of 4 main goals: containerize the root RDF-based AGC analysis for execution on REANA, integrate SnakeMake to allow efficient parallelization of tasks, modify the analysis to run from a single configuration file, enabling automated reinterpretations, and finally, extend the workflow to support NanoAOD datasets from CMS Open Data. The overall impact is a simplified, reproducible, and community-accessible workflow for particle physics analyses. Let's look more closely at SnakeMake. SnakeMake was chosen as the workflow engine because it naturally supports parallel execution, clear dependency management, and transparency. Each step in the analysis, from reading input NanoAOD files to producing histograms, is represented as a rule. This makes it easy to distribute the computation over many jobs, while REANA takes care of scheduling and container orchestration. To make the AGC analysis more flexible, several new command line options were added to analysis.py. So, a sample and file name allow processing a specific dataset or even a single NanoAOD file, which is essential for parallel execution. From hist file enables running only the plotting or fitting stages from pre-produced histograms, so you don't need to reprocess events every time. And total N events allows proper normalization across multiple files by passing the global number of events from metadata. These small changes significantly improve the modularity and scalability of the workflow. On the physics side, the analysis was extended to include a Z-prime signal model. We defined signal samples for both analysis channels and introduced consistent sets of systematic uncertainties, such as jet energy scale, jet resolution, bit tag invariation, and luminosity. And universalization parameter Z-prime norm was introduced as a free fit parameter. Both signal samples were then incorporated into their respective his vector channels for statistical fitting. This integration demonstrated that the workflow could handle both standard model backgrounds and new physics signals in a consistent way. The REANA specification file, reana.yaml, was designed to describe the entire workflow, inputs, outputs, and computational steps. With SnakeMake integration, it became possible to launch hundreds of file-level jobs in parallel, each running in its own Docker container. This parallelization drastically reduces runtime while maintaining full reproducibility and traceability. At the heart of this setup is the SnakeMake rule called run analysis. It defines how each NanoAOD file is processed into an output root file. Using wildcards like sample and file ID, SnakeMake automatically expands this rule into many independent jobs. Each job feeds its input, computes metadata such as total events, and executes analysis.py with the appropriate arguments, all inside a consistent container environment. Here's a quick summary of what was achieved. A fully working REANA workflow with SnakeMake backend was established and validated. CMS Open Data was successfully integrated, processing NanoAOD datasets from 2015 and preparing structures for 2016. The analysis framework was extended with Z-prime signal support and new features. Workflow automation was improved with JSON generation and reproducible containerized execution. And finally, the physics output were validated, showing consistent histograms and extending channels definitions with systematic uncertainties. Altogether, this lies the foundation for scalable reinterpretation workflows within the AGC framework. After adding the Z-prime signal to both analysis channels, we observe the expected changes in the fitted histograms and statistical outputs. This confirms that the workflow correctly incorporates new signal hypotheses throughout the full analysis chain. These plots show the visible effect of the Z-prime contribution in the high mass region for both channels. They serve as a validation of the reinterpretation workflow and its consistent behavior across parallel jobs. To summarize, this project demonstrates how a complex high-energy physics analysis can be fully containerized, parallelized, and reinterpretable using REANA and SNAKEMake. It successfully combines the technical and physics aspects, from reproducible workflows to Z-prime signal integrations. As an IRIS-HEP fellow, this experience also shows the potential for developing scalable reinterpretation pipelines that the wider HEP community could reuse and extend. As future work, the pipeline can be further generalized to handle additional new physics models, automatically bringing us a step closer to a truly RECAST-like reinterpretation service for open HEP analyses. That's all. Thank you very much for your attention.
Thank you, Dmytro. Matthew, you have a question?
Hi, thanks very much for the very nice talk and for this excellent work. It's great to see. You might have had it at the start of your slides and I missed it, but can you also include a link to your repository with the work that you did in the slides? Because I think that'd be excellent for people to have as a reference. And one other quick question is, you showed on the parallelization slide, you were showing two different YAML components next to each other. I didn't quite catch what the since the text is a little small on my laptop screen, I didn't quite catch what you're showing there. Can you go back to that slide and expand a little bit more on that?
Yep, sure. So first of all, there's two specification files. The first one includes SNAKEMake parallelization. So, and the second one is basically serial workflow without any parallelization, but it works as well on REANA, but it takes quite longer. So, yeah.
Okay, so it's just the main takeaway here is just that the right-hand side, the without parallelization, just has the type serial, correct?
Yep, absolutely.
Okay.
Yep.
All right, great. Thanks very much.
Thank you.
All right. Any other comments or questions for Dmytro? All right. Thank you, Dmytro. Up next is Svitlana.
Hi, everyone.
Hello.
I hope everyone see my screen.
Yeah, you're fine. Go ahead.
Perfect. Thank you. Okay, my name is Svitlana. I'm from Princeton University. My mentor is Alex Held, Oksana Shadura, and Palabiras. My topic is RECAST-like workflow for analysis current challenge, and today I will explain how we built a fully reproducible analysis workflow using REANA in the analysis current challenge context, and how we extend it with a RECAST-like strategy and a successful combined integration. A little bit of motivation. Actually, modern analyses are complex and have many steps, and we run long processing chains, create many intermediate artifacts, and we offer. And in this situation, reproducibility is essential. It lets collaborators run, inspect, and extend the analysis with confidence, and it keeps results attitude months or years later. Our goal was simple to say, but hard to do. It's make the analysis one common reproducible, portable across the environment, and easy to use when physics input change. We used REANA, a platform for reproducible containerized scientific workflow, and REANA lets us package its step in Docker or Singularity containers and run the full pipeline with a supported engine. We also use SnakeMake, and we can run the workflow only with one command and the same environment, and it will work still years. REANA also supports SnakeMake, YADAG, CVL inside container for strict reproducibility. Why REANA helps in daily work? Actually, REANA gives us full artifact management. All outputs, logs, and configuration files are saved. Selective rerun, like if we have 100 files run and 5 of them fall, we rerun only those files, and the same for us time and resources. And also it's ideal for long modular analysis. Let's talk about pipeline outline in REANA. REANA reads output file location from a JSON list. It processes each file in parallel, and SnakeMake create profile jobs. Each job run in a container and process clear outputs. Match created histograms for each sample, and we collect profile outputs into per sample histogram in a reproducible way. Combine samples to obtain stacked histogram, and we make the summary views needed for later statistics and diagnostics. We also do plotting and statistical interference. We run the modeling and limit setting steps. And for those purposes, we use two-level parallelization, per file and per sample. Now let's talk about our RECAST-like idea. As a traditional way, when the signal change, we run everything, but RECAST way is different. If only the signal change, for example, we have a new Z-prime mass, we reuse not all intermediate, we reuse all intermediate result, but we run only the final statistical step. It makes things much faster and easier to work with data. And in our work, we upload only the Z-prime signal samples, and we reuse all background histograms, and we compute limits with cabinetry, PyChef, and with combine. Constantly, we replace the signal inputs, let SnakeMake rebuild only dependent nodes, and then run the final limit rules. Everything else, like our main histograms, stay untouched and documented. Here is a list of completed mainstones, a fully reproducible REANA workflow driven by SnakeMake with each step consistent. Two-level parallelization per file process and per sample merges, clear separating or baseline artifacts and single updates, end-to-end artifact and log preserving for each debugging and review. Also, limit production using PyChef for cabinetry on stacked histogram and successful combine integration, automate inside the same workflow. On this figure, we plot the 95% CL upper limit on the signal strength for the prime mass, and the dashed line is the expected limits, and the green-yellow bands show 1 sigma and 2 sigma range under the background only asymptotion. The solid black line is our observed result obtained from pre-pseudo data. And as you can see, the best sensitivity is around 6 to 1100 GV. toward higher mass limit growth, which is the expanded behavior. About our combined integration, we convert our coffee histogram into combined ready inputs. Then we run the standard chain for combine, build our statistical workspace, and do command to get, extend, and or third limits. And also we capture logs and outputs as REANA artifacts. We also do a cross-check with PyChef cabinetry using the same histograms. This keeping the analysis bilingual in statistics with PyChef, coffea, and combine. It's similar to common collaboration practice, and technically the combined pass is a snake-made target. So rerun combine is just another containerized, and reproducible step. To wrap up, we built a containerized, one common reproducible workflow on REANA using snake file, and we design it with a RECAST-like philosophy, reuse stable intermediates, and run only the changes. We also implemented combine and cross-check with PyChef cabinetry, consistent limit with expected difference, and the whole pipeline preserved artifacts and logs. So this is an important step toward future HEP analysis that are scalable, transparent, and fully reproducible. Thanks for your attention. Some comments, questions?
Thank you, Svitlana. Any questions for Svitlana? All right, thanks again. Next up is Danylo.
Okay. I will share my screen.
Great.
Can you see my presentation now?
Yes.
Okay. So hello everyone. I am Kulakov Danylo from Ukraine. I study at Taras Shevchenko National University of Kiev, and my mentors is Mikhailo Obradovich, Arkady Lokvitsky, and Olena Karcheban. I forgot to spell the name of my project. It was DevOps and cloud-hosted database for HL-LHC FBCM detector development. So about that detector, it's future project of CERN that are building just now. It will start to operate in middle of 2030, and it's consists of different parts. And I was developing a database to store some measurement of luminometer. This luminometer, we have two luminometer at Z and at plus Z and minus Z beam axis. So we will have it looks like that, and we will have two them in two parts of. They consist of two parts, and they called half disks, and so on. And introduction. So Brill team had some database before, but that database was running locally, and that's why they lost all their data they have collected before it. And my task was to understand why they lost all their data and what to do to be sure that data will be safe in the future. And we decided with my mentors to use CERN cloud services like OTD, and also to use PostgreSQL database because it's considered as one of the most protected and so on. And as we understand, database is backend of, but we also need front end where user will be able to fill database, to check some tests and so on. Okay, about structure of information that we store in our database. You can see here that we have here half disks, and it's top part in our connected graph. So on half disk we have some DC-DC power supply model and port cards, VTRX, and also we have here hybrids. Hybrids consist of ASICs and sensors. Also, each ASIC and sensor has its own measurements, and we need to store them. For example, measurement can be different. Some measurements were done in room temperature or at high temperature, before irradiation, after irradiation, and all that data need to be stored. And also we need to compare different measurements with each other. And also, if you look at that graph, we understand that if we have connection between ASIC and sensor, it means that they have the same front-end board. That's why we should to implement that function that will forbid to connect ASIC and to path to different front-end boards. Okay, code structure. So main folder on my GitLab is equipment. We have here our backend, front-end, and also some tools that will help us to migrate from one database to another database. And that's how our front end looks like. So here we have our main page. On main page we can choose with which component we would like to work today. Sensor, 2-pad, 6-pad, ASIC, port cards, half disk, DC-DC, VTRX, and front-end boards. And also I have implemented a lot of things to show some tests or measurements plots. Like here, we can see plots from ASIC measurement. It's called gain plots. And we can see here that we can compare with each other every channel in that ASIC. Also, I implemented a page where we can understand a current progress now. So we have every step here. It's when people upload some data in our database, and also when it will be enough, we will see that we will reach our target soon. So our target for front-end boards is like 132. And when we will reach that amount, we will see it that we finished that. Also, we have simple visualization. It's easy to understand how to add something, how to delete something. We have simple colors. So green is excellent, yellow is working, and red is broken. And as I said, we have different measurement conditions like normal temperature, irradiation, after irradiation, and we can compare them by clicking one button on it. And about backups. So even if it cloud hosted, maybe there will be some DDoS attacks, or some user will use some inappropriate way to change the database. That's why I implemented backups. So on OTD web services, cron job was created. That cron job make a dump of our database into SQL file and saves it for 7 days. And how to restore our backup? So we just need to run restore.ch. We will see a list of available backups. We choose it, and it will be automatically restored. Simple and reproducible. About our operation in OTD web services, I just can't show you much more because we have passwords, we have credentials, and to be sure that it's safe, it's stored in a special way on OTD web services. It's called secrets. Also, if someone will update that database in the future, he can freely just create merge request on GitLab, and OKD will be automatically updated. And conclusions. So there was completed redesign of database, implemented some new features, plots building and comparison. Also, we found a way how to connect OTD to GitLab and implemented a way of backups, ensure our safety even in critical situations, and we can quickly restore our data and continue to work. So here you can see a link to my GitLab repository, but I think it's only accessible for Brill team. Also, I put here a README from that GitLab, and that README is accessible for everybody, and so on. And and here also is a link to my IRIS-HEP fellowship page. So that's all. I'm waiting for your questions.
Thank you. Any questions? All right, on to the next one. David? No, David. Okay. Moving on. Yurii, are you connected?
Yes, I'm here. I can start.
Thanks.
Okay. I'm sharing my screen now. Should see it.
Yep, we can.
And now my presentation.
Go ahead.
Can you see it?
Yes, yeah, you can go ahead and start.
Okay. So, hello everyone. My name is Yurii Perets. I'm Bachelor of Studies graduate from Kyiv National University of Taras Shevchenko. Here you can see on the screen presented team of my project, CMS Forward calorimeter run-free data analysis. And my mentors are Alexey Shavelov and Elena Karchaban. So you can see on the screen a few logos here, Brill project and CMS experiment. So I want to start with a short introduction into a general setup. So first of all, the general LHC orbit. And so you can see here is the CMS experiment. First of all, I need to start with a few important vocabulary words that will help us later on the lecture. So first of all, batch crossing, shortly BX, is an event where two bunches of particles pass through each other at the center of the detector. We have 3,564 bunch crossings on our LHC orbit, and time between those is 55 nanoseconds apart. So actually, LHC is not designed to have all of bunch crossings collidable. So some of them have no real signal. They're called non-colliding bunch crossings, and this would help us later. So Brill project, or the Beam Radiation Instrumentation and Luminosity project, focuses on precision luminosity measurements and beam-induced background study. The focus of our project is on the forward hadron calorimeter, as you can see here on the picture, which provides luminosity measurements for the CMS experiments. Only two of hadron forward rings are used for luminosity measurements. Therefore, hadron forward calorimeter have two counting algorithms. The HF occupancy method that is based on zero counting. So we're tracking the fraction of bunch crossings that have no energy depositions above some threshold. And HF transverse energy method that is based on the assumption that measured transverse energy sum is proportional to the luminosity. So both of our methods require corrections to account for out-of-time signals, also known as afterglow effects. We have two types of afterglow effects. Type 1 afterglow effects due to signals that originate from the previous bunch crossings, and type 2 afterglow effects arise from the activation of surrounding detector material by a colliding bunch. So here you can see on this graph, on this plot, with the red star, we have our colliding bunch. Then we have this green pluses is our type 1 afterglow, and then this exponential like decaying line is our type 2 afterglow. Another source of error in luminosity measurement is known as the pedestal. It is a constant electronic noise offset that biases our measurements. Pedestals could result in around 2 to 5% of effect on data measurements. So they should be fixed alongside with afterglow type 1 and type 2 effects. As a result, you can see here why is it important. This is real world data, and you can see here with blue dots is our observed data. With red pluses is our corrected data. Here at the bottom, or here, you see our non-colliding bunches. So there should be no real signal. In the ideal case, there should be zero registered energy. But you see that even for non-colliding bunches, we have a pretty huge chunk of values. So after the correction, the correction result in changing of 50 to 20% of maximum value. So it is very large. As I said, it is very important for accuracy to do correction for afterglow effects and for the pedestals. Okay, so current. So to evaluate the impact of single colliding bunch, we use so-called single bunch response model. This model assumes that as a first approximation, induced signal is always proportional to the luminosity of the individual colliding bunch. In current online approach, the single bunch response fractions are calculated and subtracted from all bunch crossings in orbit, and we do it iteratively and continuously throughout the whole orbit. So throughout the whole 3,564 bunch crossings. As a result, because of it, no matter where you start to subtract, the contribution from the first bunches will be overestimated and propagated along the orbit. You can see here the Monte Carlo simulations, and in ideal case, we should have corrected values and Monte Carlo true simulations to lie around 1. So it means that we corrected our values like in truly manner. But as you can see, for current online afterglow algorithm, it provides some overestimation. This overcorrection could lead to error around 2 to 3%, which is not so bad which is not so bad for online algorithm. But we need to develop a better algorithm for offline processing, so we could reach better precision of 1 to 1.5%. So this would be the talk of our project. So new algorithm. Since we treat each bunch and its afterglow contribution quasi-independently, we can have a system of linear equation and we can solve it in matrix form. One of the ways to define a best estimate on our X is to use least square method. So as you can see here, we have the same Monte Carlo simulation values, and our online afterglow still have the same overcorrection result. But for our LSQ values, we have like we have our ideal case that all values lie around 1, so we corrected them in the right manner style. So okay, in real world experiment we have parameter HFSBR, so Hadron Forward Single Bunch Response. This parameter defines how many influence on the following bunch crossings come from a singular active bunch. So as you can see on this plot, at the beginning, so first bunch, it's 1, so 100%, and then it is drastically decays, and even around 5th, it's already very small. But you have a large number, like you can have up to 2000s in more of bunch crossings, so they will stack upon each other, and it could, as you've seen, add up to a high error. So when we do our Monte Carlo simulations, we want to test this new approach. But in the real world, we don't know how closer to the truth is our HFSBR value. So to check how to simulate this effect, we add some fluctuations. We add fluctuations by adding exponentially decaying values to our HFSBR. And parameter that defines how hardly we added those fluctuations is called a cumulative fluctuation. So it is basically the sum of all exponential values divided by the sum of all HFSBR values. Okay, and here we can see, first of all, how our algorithm compared without any fluctuations. So we see that there added no bias from our LSQ algorithm, and that online afterglow algorithm provides provides slight overcorrection. This is the results on Monte Carlo simulations, as you can see. And it becomes a bit more interesting if we add some fluctuations. We can see that, first of all, a cumulative fluctuation is 2.8%, which is actually pretty large. But even with these large fluctuations, our LSQ algorithm shows better results comparing to online afterglow algorithm. And we can even add those fluctuations in other styles. So here we added fluctuations more at the beginning, and we can add more steadier decaying exponent. So a lot of effect would go in detail. And we can still here see the same effects. So LSQ still provides better results and do not overcorrect as much. So as a result, we showed that new algorithm based on least square method shows better results for offline correction compared to currently used online afterglow approach. And at least when HFSBR is fully known, the LSQ algorithm shows great results and does not provide any additional bias to the measurements. But even though new algorithm is sensitive to fluctuations, it still provides better correction results for it still provides better correction results. So thank you for your attention. Any questions?
Thank you, Yurii. Any questions for Yurii? Okay, thanks again. Next up is Mykyta.
Yeah. So, everybody see my screen?
Yes.
Yep.
Okay, thank you. So, I'm Mykyta. Hello. And today I'm presenting you a packaging HEP tools for conda-forge with mentoring by Matthew Fickert. So this project purpose was to create to use special tools for physics simulation. To be more precise, is to create these tools to be more accessible to students and to scientists, because sometimes it requires so much time and effort just to set up these instruments, and most of the scientists and students are not developers and not programmers, and they did not understand some basic principles how to do that. So this project should have a purpose to create to make such a tools much more easier to use to this. So the basic instrument which was all around working is a conda-forge, is a community-driven tool for packaging and environment management for different platforms, including Windows, Linux, OS X, and different architecture, which is x64 and ARM. It's also very beneficial to use because it's create a local environment which will only contain necessary libraries, which will not interfere in any other systems. So it will be only locally, and it will be much more easier to clean up the system after the work. Also, the conda-forge is a big, giant platform and have a lot of tools to use. So it will be really good to contribute here. So also, the conda-forge is used Rattler build as packaging tools which using a Rust. So it should be very fast, and it also have configuring files with a recipe.yaml, which is pretty comfortable to use. It have a syntax kind of similar to JSON, but is also really readable for a human. And also, you can specify which command can be used on different systems and different architectures, and even download other packages to depend on. So actually, this project was contributed to a library called Acts, which is to be more precise, it was used only Acts core library which was contributed to conda-forge. During the project, I've learned how to create a Rattler build for this library specific for Linux and Apple on Silicon ARM64, since it's the only two platforms which is currently supported by this library. But also it can be potentially used in other platforms. We'll see how next will going on. So the final result in the project was created a pull request to conda-forge recipes, and you can see here there is an release info that we have already 200 downloads, and we can be downloaded on Linux. Arch 64 and Mac OS OS X Silicons. As I mentioned before, that was only implemented core library. There is also a discussion to create in a more intercording builds to additional builds for plugins. So here is an example how it all works. So first of all, we generate a workspace which will contain all of our libraries. Then we actually add in our X core, And we can see here that it actually downloaded and it weighs about 3.5 megabytes. So it actually works and can be used in any other different researches and any other stuffs which uses this library. So in final result, I can say that this during this project, I learned how to create a recipe, how to create a contribution to a big conda-forge project, and also I've already contributed to conda-forge packages that other people can use this instrument to their researches. So actually that's it. Thank you for watching. Any questions?
I first just wanted to say thanks very much, and that I appreciate getting to work with Mykyta, and I think I just wanted to reiterate one of the points that he made, which is that what I think his work here was really great in that it also allows for extensibility into the future. So not only is this kind of a nice effect that comes from having people be able to trivially install really powerful software now, but it now opens the door for extending and building new tools on top of that that can also be distributed. So thanks very much for your nice work.
Yeah, thank you too.
Thank you, Mykyta, and thank you, Matthew, for your comments. Any other questions? All right, moving on. Vladislav.
Yeah, hi. So give me a second, please. Okay, I hope you see it.
Yeah, we can see it just fine.
Yeah, okay. So yeah, hi everyone. I'm Vladislav Yankovsky, and now I am and my master at the Russian International University of Kiev, and my mentor is Andriy Usachov from NIHEV in Amsterdam. And so my topic of work is displaced vertex finder on GPUs for LHCb detector. Okay, so first of all, we talk about the motivation, why we do what we do. So for now, we can say that there is a lot of new physics scenarios which posit the existence of new so-called long-lived particles that could help explain some puzzles in physics, for example, like origin of dark matter. So these particles can be produced in high-energy proton collisions at LHC and can be detected by the LHCb detector. So to do this, we need a special algorithm that can quickly identify such so-called displaced vertices where these particles appear. So the main goal of this project is to write such algorithm to find some displaced multi-track vertices with anomalous topologies. So let's talk about the software I work with, namely, the work with mainly. It's the HL-LHC or high-level triggers. So what is this? Now the LHCb detector is capable of reading out a maximum data rate of 40 terabits per second. So this is the huge amount of data which we need. If we don't need it, most of them it's like the trash. So we need filter it, and it's done by the two software stages, which is the HL-T1 and HL-T2, which you can see on this figure. So the most interesting for now, for us now, it's that HL-T1 in run 3 was improved by implementing it on a GPU via Allen application. This is actually this application on which the algorithm of GeoFinder will run, and it's give us opportunity to run it like on the CPU and on the GPU. So a bit about the detector and about the algorithm. So here we can see the scheme of LHCb. So unlike so-called like 4-pi detectors, which is CMS or Atlas, in which the collision point is surrounded from all sides, LHCb is only a single arm spectrometer, which is designed because of features of specific features of formation via drones, which is the main idea was this experiment. So the idea is these via drones are like format in the neither forward or backward cones. So this is why we built this detector in this way. Okay, so this design allows the LHCb to register signals from the decay of these long-lived particles into the standard model particles. So we can do it with high precision and resolution. And for us, the most interesting is the first detector, which is the weld detector. So we can see the schematic of this of representation of this detector, which consists from the 52 models for 26 from the top and bottom part. And here we can see a lot of tracks, developed tracks, which is the used for reconstruction vertices. So we can see here that most of the tracks belong into the so-called primary vertices. So we can, and this is like about 80% of all tracks associated with this primary vertices. So what is this? We can see the schematic of such tracks, and using these tracks we can reconstruct two main types of vertices in this work. It's the primary vertices and the generic displaced vertices. So the primary vertices is located close to the beamline. Beamline it's a tube where protons or ions accelerated and collided, and we can consider this primary vertices as the point of interaction of these protons, or like some kind of decay of short-lived particles. And the next one is the generic displaced vertices, which is on the distance from the beamline and can be considered like the decay of LLP particles. So this vertices which you want to find, actually. So the algorithm itself, like written in the form of some stages, and on the first stage we need to build so-called seed vertex. How we do this? We compare every two tracks in the event and check whether they close enough according to the chi-square criterion, which is the chi-square criterion for two lines. And if this is true, so we build the seed vertex, and it has its own coordinates, like the value of this chi-square. Number of tracks for now it's 2. And also we calculate this error matrix, which is the covariance in form of covariance matrix. So then we check what are the other tracks which is belonging to the seed vertex. We also calculate the distance between them. Also we calculate the chi-square in form of chi-square from the point to line. And if so, we just add this track to the vertex and feed it again, and we obtain like updating of this vertex, like the coordinate, the chi-square, and the number of tracks become bigger. So there is also the most one of the most important stage. It's like the merge vertices. Why we do this? If we talk about the primary vertices, such objects are characterized by a large number of tracks belonging to them. So when we construct the vertices by pairs of tracks, we will see the large number of close close to each other, like this seed vertex. And we can say that most of them, which is close enough, they belong into one primary vertices. So we need this stage to merge such close vertices to reduce the number of them. So we just calculate the distance between the all pair of seed vertex and also calculate the chi-square, also in the form of the distance between two dots, let's say. And after that, we build the new common vertex, which has all common tracks, and also we feed it again. So after that, we will see like this set of vertices. Okay, let's move to the results. But first of all, I want to talk about the algorithm, which was like inspiration, or like, and it will be helpful for future. It's PV Finder, which is already used in LHCb, and the main point that it's written on the GPU, and this reconstruct the primary vertices only. So in future we will use we use this one for like inspiration for my algorithm, because there are different approaches to find these primary vertices, but it's a good point to see where we can use these CUDA blocks and so on to implement the GPU calculation. So here you can see the like coordinate of primary vertices in one of the event, and we can use it for like visual comparison in future. So what we have after the first stage of building this GDV, the first concept was that we can use all tracks like multiple times. So it's useful for like first integration of the algorithm in the stack, LHCb stack, and to test whether it's work okay. And we can see that there is like a lot of these peaks. On the blue line, it's the GDV algorithm, which is I wrote, and the red one, it's PV. And we can see that there is actually a location of PV corresponding to the location of peaks, which is expected to us, because as I said, there are a lot of closed peaks, a lot of closed vertices, which just correspond like one vertex. So this is why we need this merge stage to make them one. But first of all, we wanted to make it more optimization, so we choose the approach when we use each track only once and like label it, like marked it, and the point is that you can see that these peaks are still, and it's really good find these primary vertices. So it's still very sensitive to these primary vertices. So it's good enough because we significantly speed up the algorithm and don't lose any precisely. So after we make the merge stage, we see some kind of these sets of vertices. So there is the GDV and PV, and then we can like make the filter for these primary vertices, and then we will see only the GDV which we want. So this result, which we can see, it depends of some kind of parameters which we can tune in future. It's the parameter of how close the two vertices should be to match them. Also the method of calculating the common coordinates between that two vertex which we want to merge, and also the fitting parameters, which is a lot of thresholds parameters which we can switch, make lower or higher restriction. So yeah, there's like some kind of room for improving, but we need to find how already this algorithm works, what is his effectiveness. So for this purpose, we use the primary vertices as a metric of accuracy. How I do this? We make for the GDV the restrictions as the simple as for primary vertices, like the minimum number of tracks for all vertices and the minimum allowed distance from the beam line, or maximum, sorry. So after that, after we make these constraints, the GDV should find only primary vertices. So here you can see the blue, it's a primary vertices which find by the GV finder, and red, it's like the PV finder. So we see that they most of them close enough to actual, but there are still some kind of shifted vertices. So we can calculate the distance between them, and yeah, also here is the same picture, but for x and y coordinates. They are not so close, so that's why I show only the z coordinate. But yeah, here we can say the like some kind of numbers of precise. So here we can see the actual coordinate of the reference point, like the primary vertices, and there is like nearest point of my algorithm, which is fine. And we can see that there is tracks with vertices with the most tracks are finding quite good, like with a small difference. But there are still some kind of vertices which has lose some tracks on some stages. So we can find this losing, and in future we will increase the accuracy of this algorithm. But for now, if we see that tracks which the vertices with most tracks, like reconstructed quite good. Okay, so we've talked about some of achievements. So for now, we have this GV finder algorithm and monitoring model, which give us the visual comparison, and the algorithm which just make all these three main stages. So this algorithm like implemented in the ALEM, which I said, so it's give us opportunity to run it on CPU and GPU, and also we like calculate the accuracy of vertex reconstruction system, and for now it's like in this range, but it's still a lot of room to improve. So this done for me. Thank you for attention. So you're free to ask any question.
Thank you, Vladislav. Any questions or comments? All right, thanks again.
Okay, thanks.
I don't see Helen EX connected. Devin, are you here?
Yeah.
Yeah. Why don't you go ahead and share your screen?
All right. So I worked on accelerating the HL-LHC particle track reconstruction through various methods, and my mentor was Dr. Belytskyi. Why this matters, it's just HL-LHC has very high collision rates, and it's very slow, and we want a faster, smarter way, saving time. And so I kind of, with help with my mentor, we came up with some ideas. But first we understand how it works now. They start the inner seed layers, and they propagate them outward using the Kalman filter, which is kind of the standard. in track building, and they kind of just build a bunch of tracks and then prune the ones that score lower. And this struggles because you have to build so many tracks for each seed, and so that could obviously get very slow at high amounts. And so we kind of, this is why we came up with other methods. So one approach was a collaborative track building. So instead of each track propagating itself and just doing multiple iterations all by itself, we wanted a way for each track to share a like physics-based score with other tracks, and based off of which has the better score for a certain hit, they would claim it. So instead of just having these tracks just build themselves and trial and error themselves, they can get feedback from other tracks building alongside them. So maybe they'll learn which hits to stay away from because it's fits more to some other track, and it can really prune branches earlier or help other tracks branch into the right direction. Another approach we tried was instead of just using the standard Kalman filter, we wanted to try other commonly known algorithms for specifically like maze solving algorithms, and seeing if we could implement them for this problem set. And just a quick clarification before I show more graphs. They're going to show parallel versus sequential. Parallel, they're both technically ran parallelly through multiprocessing, but I refer to the collaborative approach as parallel. And so this is like the comparison of just alternate branchers. As you can see, A-star and Hungarian are rival the standard, which is EKF, and some of the other slower methods do still show promise, but not nearly as much as the A-star and Hungarian. And these were built off of from the ground up, so not all are perfect and have a level of MSC, but it is a level of MSC that they all kind of equally share. So it's not like any are wildly inaccurate compared to each other. And then with implementing the parallel approach or the sequential or the collaborative approach, you're able to see that for the much longer processes, the parallel does speed up the times, but for some of those faster ones, it does slow it down a bit. And so, but it does keep a relatively similar MSE to the previous, if not improving it. Just a quick speed up. The highest speed we saw was 128%. The lowest was 60%, or negative 60%. And so this showed promise with the collaborative approach. And so one state-of-the-art track builder now is the library MKFit. So after getting this conclusion that collaborative approach did have some merit, I went to apply some of the techniques used to the library MKFit. And running that, I got a speed up on the higher threads compared to the base MKFit. And both of these while maintaining 100% accuracy. And they both do use multiprocessing. And this is especially promising because the scoring function for the collaborative approach is not optimized based off of all the physics metrics that it could be, or it's not, the scoring function is not as optimized as it could be, and it's still showing promising results. So an optimization in that area could yield even further results. So in conclusion, parallel/hit sharing implementations show a lot of promise and potential speed up, especially at those high pileups. And other algorithms are viable in track reconstruction, not just the standard Kalman filter. And thank you for your attention, and are there any questions?
Any questions for Devin? Thank you for your talk. All right, everyone. That's all we have for today. Thank you to all the fellows for their work. Thank you to all the mentors for their work as well. That's all for now. So thanks.
Thanks. Bye.
Bye.